Hello everyone, in this video we have a second order reaction inside of a batch reactor. So that could be two molecules of some species called A react to form a species B. What we're going to do is try to write a mathematical expression that helps us understand the kinetics of this reaction as it proceeds from A to B. We're going to think about d number of moles of A dt, so how does the number of moles of A change as a function of time? And we're also going to look at conversion dx dt. This capital X is conversion. That is how the reaction progresses from A to B. So number of moles reacted divided by the total number of moles that we started out with. So at the initial time point, conversion will be 0, and then at the end of the reaction, conversion will be equal to 1. In this batch reactor, we're going to assume we have a constant volume. That's a capital V, constant volume of the reactor, constant temperature in the reactor, and we're also going to assume that this is a well-mixed reactor. And that will help us make some assumptions about how the reaction rate is proceeding, because we'll know that the concentration of all the species at this part of the reactor will be the same as the concentration at this part of the reactor. Our steps for solving this problem: first, we're going to write a mole balance. And that is going to be this term right up here, this dNA dt. We're going to try to characterize that equation first. Second, we're going to write this differential equation in terms of our conversion. That's our dx dt. In terms of conversion x. And 3, solve the differential equation. Okay, we're going to start out with that step 1, which was write a mole balance. So that mole balance is going to start out with dNA dt, change in number of moles of A as a function of time, and that's generally going to be equal to how much A comes into the reactor minus how much goes out plus generation. So how much A is generated or consumed within this reactor. And since this is a batch reactor, there is no inlet or outlet on this picture. In and out are going to be equal to 0. Basically, the idea of the batch reactor is you load it all at time equals 0, nothing happens, and then once everything's loaded, the reaction will start progressing. So that's going to be our assumption. What we're left with after we get rid of in and out is the generation term. So our generation term is going to be equal to the rate of reaction. This is the amount of moles reacting per time and per volume. So we need to multiply this by the volume of that reactor. That's our capital V here. We have a second order reaction. And so that is going to be our reaction of A is going to be equal to negative K, our rate constant, times concentration of A squared. And that second order reaction means we have this squared at the top here. That could come about by two molecules of A having to collide together to form a molecule of B. So now we can put this together into our differential equation. So we get dNA dt is equal to minus kCa squared times our volume. We can rewrite this equation all in terms of concentration by moving this volume term to the other side of the equation. So that becomes 1 over V d number of moles of A dt is equal to minus k Ca squared. And if we bring this V inside this differential, this will turn into d concentration of A dt is equal to minus k Ca squared. Here is our starting point, our differential equation that we got from the mole balance. I'll point out that we were able to do this maneuver, bringing our volume inside of the differential equation because we assumed our batch reactor has a constant volume. In this problem, we're going to solve this in terms of conversion, but since we're here, let's just solve this differential equation right now in terms of concentration. To solve this differential equation, we can move all of the Ca terms to the left and then the other terms to the right. dCa divided by Ca squared is equal to negative k dt, and we can take the integral of both sides here. We can integrate both sides of this equation. We're integrating the left-hand side from Ca0, this is our initial concentration of A, to Ca, that's our concentration after a certain amount of time, T. And on the right-hand side, we're integrating from 0 to T. So on the left, this integral becomes 1 over Ca with a minus sign that we're evaluating from Ca0 to Ca. So that is equal to negative 1 over Ca minus 1 over Ca0. And on the right-hand side, this one's a little easier to solve. That's just going to be minus Kt. So these negative signs out here cancel out, and we're left with 1 over Ca minus 1 over Ca naught is equal to K times T. And often in these problems, we want to solve for T. That's basically saying if my goal concentration of A at the outlet is a certain value, how long will it take me to reach that conversion? So we're solving for T based on some of the other conditions. So let's write this out. T is equal to 1 over K times 1 over Ca minus 1 over Ca0. And so that's our solution to this first part of the problem. Now I said step 2 of this problem, if we go back here, step 2 is write this mole balance in terms of the conversion x. Writing in terms of the conversion is often a convenient way to solve these problems, so we're going to go through the same solution this way. We should end up with the same answer at the end, but it is useful to learn how to do it in both ways. So let's start with this differential equation right here. I'm going to put this equation up in the left-hand corner. Let's not forget about that equation. We're going to come back to that once we have an idea about conversion. Our conversion x is equal to the number of moles of A reacted divided by the moles of A fed to the reactor. So moles of A fed to the reactor is going to be equal to Na0. Na, this is the number of moles in the reactor at a certain time. We'll call it at time t. And then so the number of A reacted is going to be the amount that was fed minus this number of moles in the reactor. So this is going to be our numerator in this expression. This is equal to moles of A reacted. So then we can write x as Na0 minus Na divided by number of moles fed, Na0. We can rewrite this by solving for Na in this equation. So that becomes Na0x is equal to Na0 minus Na. And then we can bring this to the other side of the equation. We get Na is equal to Na0 times 1 minus x. So that's a common expression that we'll use to think about conversion in terms of Na. Now our differential equation up here is in terms of concentrations. For this problem, since our reactor has a constant volume, we can divide both sides of this expression by V. So multiply by 1 over V over here and 1 over V over here. And that'll give us Ca is equal to Ca naught 1 minus x. And this is something that we can plug directly into this differential equation. So let's do that on the next slide. So to rewrite this equation in terms of conversion, let's first plug in Ca to both sides of the equation. So on the left side, we get d dt of Ca naught 1 minus x. And let's evaluate this expression here. Ca naught we can pull outside. Derivative of 1 minus x is just going to be negative dx dt. So this is Ca naught times negative dx dt, and I'll just pull the negative outside. Ca naught dx dt. So that's our left-hand side. The right-hand side we can just plug in. So I'll rewrite this as negative Ca naught dx dt is equal to minus k Ca naught squared. So that's the first term, 1 minus x squared. And so now we can start trying to solve this equation. First, I'm going to cancel out these negative signs. I'm also going to cancel out this C naught with one of these two Ca naughts. So we get dx dt equals k Ca naught times 1 minus x squared. All right, here is the starting point. Now that we've rewritten this equation in terms of conversion, let's solve this equation. So first step is to separate the variables. We get dx over 1 minus x squared is equal to k Ca naught dt. And here we're going to integrate the left-hand side from a value of conversion of 0. That's when the reactor starts running. No A has reacted, up to a value of, we're going to call it x. That's going to be the conversion at a certain time t, which is going to be on the right-hand side of this integral. So let's start with the hard part first, this side of the equation. So integral from 0 to x dx 1 minus x squared. I'm going to solve this with a u substitution. So let's set u is equal to 1 minus x. And then we know du is going to be negative dx. So let's plug in these two values for this integral. So that gives us integral. I'm going to leave off these signs just for, leave off the bounds just for convenience. We get minus du divided by u squared. If we evaluate this indefinite integral, that'll bring us to 1 over u, which we'll evaluate from certain values. And now at this point, I'm going to plug back in for 1 minus x. So we end up with 1 over 1 minus x, which we are evaluating from 0 to x. When we plug in the bounds of this integral, we get first 1 over 1 minus x minus 1 over 1 minus 0. So this is just 1 over 1. It's a little convenient here to combine these into one fraction. So I'm going to multiply the top and bottom here by 1 minus x. So we can combine these two together. And when we subtract here, we just end up with 1 minus 1, which will go to 0. And then this x's sign goes to positive. So we end up with x over 1 minus x. So that's the left-hand side. The right-hand side I can do in one step. So that's just evaluating this integral will become t. So k Ca naught times t. And now we can just plug these two sides into the same equation. So we get k Ca naught times t is equal to x over 1 minus x. And as we did before, it's a little nicer to write this in terms of t. So we can basically say at a certain value of the conversion of our reactor, what is the time? How long does it take to reach that conversion? So for instance, if you want to get 80% of your A reacted into B, how long does that take? And you can solve this equation for that. So t is equal to 1 over k Ca naught times x divided by 1 minus x. So returning to our starting point, we had this second order batch reactor, 2A goes to B, and we assume this is a constant volume, constant temperature, well-mixed reactor. We first wrote a mole balance and solved a differential equation for concentration, and that was this solution right here. And then we solved the equation again in terms of conversion, which was right over here. And for a little bonus, I told you that these two ways of representing this are equivalent, so let's just prove that on the next page. So earlier we had that x can be written as Ca is equal to Ca naught times 1 minus x, and we're just going to plug this into this top equation and hope that we get the equation at the bottom. T is equal to 1 over k, 1 over Ca naught, 1 minus x, minus 1 over Ca naught. And now in order to combine these two fractions together, I'm going to multiply and divide by 1 over 1 minus x. So let me remove this parenthesis. 1 minus x, 1 minus x. And so now we can subtract right here. So now when we combine these two fractions together, we get 1 over k, 1 over Ca naught, 1 minus x is on the denominator, and on the numerator we have 1 minus 1, so that'll go away, and then again this x will end up on the numerator just like before. And now if we pull this term out of the parentheses, we get T equals 1 over K Ca naught x over 1 minus x. And so there you go. These two representations are the same. So you could do it either way, whichever way you like better. Hope you enjoyed this video. Thanks for watching.